All right, so a little bit different than you're used to. Okay, so if we have which, all right, let's talk about this. Okay, if I am in the rectangular coordinates, right, and I asked you to compute the area under this curve, okay, and we go, let's say it's just from here to here, right? We're actually computing this here, correct? Okay, so that's rectangular coordinate grid. Polar coordinates are different, and it's pretty handy because it gives us a different way to compute. Okay, now if this is, yeah, rectangular, Cartesian, some people call it the XY plane. There are probably other names I'm not thinking of at this point. But if we do this in polar coordinates, okay, and let's just go from zero to pi, or pi over 2, whatever it is on this one. But what you're going to get, it's not area under a curve anymore. Okay, it's the area contained in the curve. Okay, there's the difference. So, and the way it's measured is it's what we call a sweep. Okay, so the area will actually sweep when you integrate. Instead of going from 0 to 1 or whatever this is, right? You're accumulating area that way. This, we start at 0 and it accumulates this direction.
So your integral is going to look like?
It's still going to be, it'd be like the integral from 0 to pi. Right.
It's just infinite lines of different lengths until it comes back to 0?
Conceptually, no. It's the area of each one of these pie slices.
Okay.
And you make those pie slices infinitely small, or make an infinite number of them, and then you get your accumulated integral area, right? So you're actually doing the area inside a curve now instead of the area under a curve. Okay, so kind of a conceptual thing to keep in mind. The formula. Okay, notice we're in trigonometry terms now, alpha and beta instead of A to B, right? This distinguishes it from rectangular coordinates. So this would be your equation, like R equals sine theta. You put sine theta in here. Okay, so some people also write it like this. Just so the thetas match up, that's F at theta. Okay, so the only thing that gets people really is the 1/2. Okay, so be careful that the 1/2 has to be in there. It could take time to explain that, the why, but we don't need to. All right, so you get this concept, right? Good? Okay, all right, let's try a couple.
Can we do the flower thing?
Let's do, we will get there. Let's say we have R equals 4 sine theta. Okay. And that's just what I drew up there basically. Compute the area of the right semicircle. So what point is that? So if we want the area of the right semicircle, right? This circle has a diameter of 4. Okay, we want to calculate the area in there. Can you do this with geometry really easy, right? Pi r squared, radius is 2, right? Okay, so we know we can do geometry here if you want to. It's always an option. Frankly, it's the easy one, right?
What they thought.
No, no, they will not. Okay. Part of what you want to do if you're in a mathematics-based career is make it as easy as possible on yourself, and we actually encourage that. Right? So the easy route here is to use geometry, right?
Alright, let's do the hard route.
Now let's see the hard way. Okay. The question is, when we write out our integral, 4 sine theta squared, what are, this is what I told you, what are the start and end? Okay. Right, so here, our radius is 4, right? So your reasoning is good. Where is sine theta 1? Yep. And where does it start? Right, 0. Because if you plug pi over 2 in here, sine of pi over 2 is 1, and that gives us a radius of 4. So you have pi over 2, 4. Okay. So you think it's pi, right? You're like, okay, that's half of a circle, it's pi. That's what I'm telling you, you got to be really careful with that assumption. Because a lot of these curves repeat at pi units. Yeah. Okay, so if I put pi in here, I get 0, right? That's back to the beginning. We've just repeated. Start repeating. So, but if we only want half of this, 0, pi over 2. Okay. Anybody think of a way to do that? Okay, 4 squared is 16, right? 16 over 2 is 8. Sine squared theta. Anybody? You don't remember your trig identities? Shame on you. I don't either. This is not going to be a question that we do by hand. If you're asked for that, it would be a set the problem up, or it would be use the calculator. Okay, so, but if you did need to do it by hand, this is the identity you would use. Cosine 2 theta is 1 minus sine squared. You just kind of edit that a little bit, and you can do that integral, right? So, there you go. All right. But again, the trick there, get the right integral limits. Okay.
So
Good.
for in polar area, are we ever going to be doing integrals by hand?
Yeah, you can.
Yeah.
But the problem comes with the squared. It creates a lot of problems with trig functions. right? So a lot of times we will use a calculator. The area, if it's a polar area problem, and a free response that they require an answer, they usually ask you to use a calculator.
So that way you're not spending any.
Correct. Because the calculus, I mean, beyond that, you've done, right, a ton of it. All right, moving on. Let us calculate the area of one petal r equals sine. So you have no idea what this looks like, right? Of course we do, because we drew it up there earlier, but if you're on like the AP exam, you're thinking, what does this look like? Maybe you have a calculator, maybe you don't. If you don't, and you don't want to graph it by hand, how do you figure out what your integral limits are?
I bet you're in trouble.
Hmm? Yeah, you need to figure out where sine 3 theta equals 0. Right, because that's where the petals form.
And you should get 2 answers for that.
You should get 6. Okay. So where does that occur? We're thinking through this algebraically. Okay, so if I put 0 in, I get sine at 0, right? Where else is sine 0? Pi? Right? So 3 theta has to be pi, right? So pi over 3. And that's actually our one circuit, our first petal. Right. So what we have here now is that. Right, so, and if you kept going, you would get pi over 3 to 2 pi over 3. That might be down here, then 2 pi over 3 to pi would finish it out. Right. So thinking through where the zeros of some function are is a good algebraic method to find those integral limits.
So is that basically saying that your coordinate scale is within the basically the pi slice of a unit circle from 0 to pi over 3?
Yeah. Yeah, basically. And then again, that's a calculator problem for us mostly. There is a trig identity we could use. It's nasty, messy, but we're not going to worry about trig identities. Okay. So, what if I wanted to calculate all 3? Yeah, you could do that. Correct? Yeah. Or we could do this. Okay. Both very legitimate methods. Correct.
How do you know algebraic, like how do you know how many times it's going to repeat before it just starts repeating like same shape? Because like obviously you've got that first petal, but then there's 2 other ones that are going to contribute to that area. So how do you determine that algebraically?
When you find the zeros, right, you get 6 of them. No, you get 4 of them actually. I would plug in, let's say, pi over 6 So pi over 6 will give us this point out here. And then you come to pi over 3 to 2 pi over 3. If you plug in, let's say, 1, 2, 4 pi over 6 or something of that nature to get this point. And then something here. And if once you get past those, it'll start repeating. Because these will be different coordinates, right? The coordinates will start repeating.
Right.
So
So you just plug in different points.
that's why I would approach it. There's probably a better method. Yeah, but for sure. Okay. All right. Okay. Let's look at area between two curves.
What's most common in those, what one's the most common thing that shows up on the
For area,
yeah.
things I'm showing you. Yeah. Okay, let's say this circle radius is 1, that's the unit circle, right? And then we have another circle, 2 cosine theta. That's going to be this circle. Whoa, that's more of an ellipse, I guess. But, whatever.
So you're basically solving for the area of 45
Well, there's lots of questions we could ask with this one. Yeah. So we could ask, what's the area inside r equals 1 and r equals 2 cosine theta? Like that would be here, correct? And how would we solve that?
Right minus equal to 1/2 integral right minus left.
When do you where the red one hits 0 on the left side? It's line,
0?
yeah, 0 on 1, and then 0 on the left side.
Right. You have to subtract 1 intersect.
Oh, yeah, you subtract 2 cosine theta minus 1, and this is where that this formula.
Here's the problem with what we're thinking. When we sweep these circles, these intersections, okay, so let's say if I did the black circle, this is, I think that's negative pi over 3.
You only sweep from the word.
Yeah. So this is negative pi over 3. This is pi over 3, right? If I sweep that area, I've left out a little sliver right there, right? So how do I count that? Because I can do the integral from negative pi over 3 to pi over 3 of r equals 1. But I've left out a touch of a sliver there with the red circle, right?
Well, when you do it,
Not the red one.
when you do it like that, don't you have too much area then too? Or don't you account for the whole right side of it?
It sweeps from here to here. Yeah, so none of this is counted in it. Right, so we've got this area, but we've got these little slivers here. How do we figure those out?
You just do the integral from 0 to negative pi over 3, 0, pi over 3 is the right circle.
Yeah, if I put 0 in, I get 2. So 0 that on this circle is actually out here. Right?
Well, then what's
Pi over 3. What's that value going to be? So what we want to figure out is if this is negative pi over 3 here, right? Is that also 2 pi over 3 sweeping this direction? Is that right? So if I put pi over 3 in, the cosine of pi over 3 is 1/2, correct? So I get 1. If I put pi over 2 in, so this is 1. What if I put pi over 2 in? I get 0. Okay, pi over 2 is here. And then this would be 2 pi over 3, right?
wouldn't it just be the same thing as already?
If you're sweeping from the origin, you started here, you swept this little sliver, and you're sweeping this all the way out to here. Right? You see how that, yeah, you see how it makes a little bit of a difference? Because if we started at 0, 0 sweeps here across, right? But if we start at pi over 3, it starts with this line, and it gets this little bitty spot, and then this little bitty spot. And now we have our complete area for that.
So how did you get to do pi over 3?
Okay. I'm looking at the intersections, right? On the circle r equals 1, 0 is here, correct? So if I go from 0 to pi over 3,
Oh, okay, okay.
but if I go from here and want to sweep up, that's negative pi over 3.
Yeah, I get it.
But if I'm on this circle, it's pi over 3 and 2 pi over 3 because of the way we have to sweep it. So again, what do we see? That these are the kickers in figuring everything out, right? That should be a 3. Okay. So, yeah, you got to think, right? This is the way these roll. Okay. How would I calculate this area?
The area of that circle is just move right here.
You're close. Okay, we're going to use this again, right? So, because we want to take this circle, but if you think about it, if I do the red from negative pi over 3 to pi over 3, that gives me this pi slice that we already figured out plus this, right? It gives me this circle with that sector in it. Okay, so we start here and we sweep out this circle, and it doesn't have these little slivers in it. Okay. What do we need to subtract out? This one, right? So you gotta think, like, what is the swept area actually creating?
So for that one, it doesn't
Okay.
matter that you're missing the slivers because you're just not
Uh-uh.
considering the area.
No, you don't have to worry about them this time. Yeah, because this right here gives us this whole area without those slivers.
Right.
And then we can come back and this gives us this area. So we've just calculated that little lobe there, our crescent moon. Okay. And again, the setup's not hard once you figure out what you need to do. You just got to figure out what you need to do. Okay. And it's a challenge because you're so used to thinking in rectangular coordinates that it's kind of screwy. So, yeah. Could we also figure out the area over here? Yeah, we could. Right. A little bit more of a challenge, but it could be done. Okay, those are the 3 examples for area. We're gonna naturally work on this quite a bit the next few weeks because it is kind of a mind shift. Kind of like series for you, right? That's kind of a mind shift in calculus terms. Well, this is too, so we'll hit it pretty hard. Okay. But tomorrow's arc length and slope of polars in them were good. We've learned everything. You'll know everything. Yeah, right? Okay, so there you go. Give these problems tonight a shot. You're going to be using the calculator a lot probably. Okay, so, and I didn't print it because I was not on top of things this morning. And then we'll talk about it tomorrow.
Tell me those words.
Yeah, you're gonna, I know I did.
Still want to take that test off that I gave you?
No kidding, right?
Okay.
Still kind of big.
Okay.
Well, how much fun for you?
Okay, there you go.
What was the one that you put in there?
9 part 1. Okay, notice these 3 responses are from chapter 7 and 8. They are BC questions.